All right, so I evidently hit stop when I meant to hit pause. Definitely going to blame that on no one at all. So the way we deal with diprotic or multiprotic acid, what does that even mean? Multiprotic acid. Sounds like some sort of disease. Well, he's got multiprotic acid building up in his veins. It's not good. It just means that there's multiple hydrogens that can be removed. And so we would write the reaction and then leave a gap. And each of these has its own Ka. This one's usually called Ka1 because it represents the first hydrogen that's popping off. Look at that amazing handwriting. So illegible. And then what do you think the other Ka is called? Ka2. Ooh, what a crazy idea. Nope, that's wrong. Just wrote the wrong thing. There should be no H here. Product has no H, Russell. Welcome back. So a couple funny things about multiprotic acids, other than the fact that you get to see multiprotic acid, is the first part is the same as we've been doing. Bam, ba bam, bam, bam. You know, let's just throw some fake numbers up here. Fake number man. That is a lame number. He said 1. He didn't even say 1.0. I'm throwing a 0 on there just so there's some amount of sig figs that it's not a guess. So right, we'd subtract x, we'd have 0 plus x, 0 plus x. We fill that stuff in, x squared equals 0.1 and a Ka, and then we'd solve for x, right? And let's pretend that we solved for x, and the answer was 5 times 10 to the minus 4th, or something like that. That doesn't look like a 5. Let's pretend that's the value for x. So that's the first reaction. Typically, they don't give you any data on the second reaction except for the Ka value. So they give you the Ka value. This represents what? It represents the amount of hydronium and the amount of monohydrogen sulfite. That might not be the right name. I think that's right. Represents the amount of HSO3 minus 1. Check out the second reaction. Is there HSO3 minus 1? Yes, there is, right here. So the initial amount of this would be 5 times 10 to the minus 4th, because it was made in the first reaction. So it's now the initial part in the second reaction. Do we care about water ever in any of the reactions, really? Only if we're real close to 7 as a pH, then we care about it. Is there any SO3 left over in the first reaction? No. Is there hydronium produced in the first reaction? This also has an initial value. And then we do our whole minus x plus x stuff. I feel like I'm dancing up here. Minus x, 0 plus x, plus x. What do we usually assume with x? It's super tiny to not matter. So let's substitute some stuff in here and watch how easy the math becomes in a second. So Ka2 equals the amount of SO3, which is x, times 5 times 10 to the minus 4th, plus a tiny amount of x we ignore, divided by 5 times 10 to the minus 4th, plus a tiny amount of X we ignore, what happens? We get some canceling because we have 5 over 5, right? And the X value equals the Ka2, whatever the Ka2 is. So we don't actually have to do math for the second protic acid. The Ka2 value tells us how much. We just say, here, we're just handing you the answer. Which is pretty nice. Very nice of them to say, here's the answer, don't do any work. So if you have a multiprotic acid, they're telling you with the Ka2 value how much of the anion is present. If it's a triprotic acid, then there's another reaction, and that Ka3 would tell you how much of the phosphate or phosphite was in the water. It becomes incredibly tiny pretty fast. Right. So here we have a Ka1 and a Ka2 for vitamin C. I always struggle to say this word. How would you say that? That there, yeah. Ascorbic. I've always felt like I'm saying it wrong. Like there's a letter missing. I don't know what it is, but ascorbic just sounds like someone's wrong. Like they didn't know what they were doing. So here's a lot of times I see a Ka2. So I will write H2A. You see what I'm doing there? Instead of writing down ascorbate, I am just writing down, look, there's 2 hydrogens and an anion. The anion's big. I'm not writing the whole anion. I'm just 2 hydrogens. We've got to take them off one at a time. Oops, made my charge wrong. And H3O. So that's my first reaction. And the second reaction, that negative Ha, reacts a little bit more. Makes some more anion. But like we were just saying, the Ka2 is going to represent how much of the second anion. So I can right off the bat tell you that the final molarity here is that. That is the final molarity of A. 1.6 times 10 to the minus 12th. Because when I get to that final point, the amount of hydronium and HA will cancel each other out, and we'll just have the Ka2. So that's the easiest part about the second reaction, is this value, the HA, will be divided underneath the H3O. They'll be the same value because they'll come from the previous part. They'll both be X in the previous part, so they'll cancel each other out. The calculation for pH, though, is going to be dominated by the first reaction, because whenever we're doing a pH calculation, do we worry about the strongest or the weakest in the solution? We're going to look at whatever acid's producing the most hydrogen or whichever base is taking the most hydrogen. So I didn't even worry about my masses yet. What do I need to do there? 500 milligrams need to be changed into grams, divided by the molar mass, so I've got moles, and then divided by the volume, so I've got molarity. There's a lot of little work that's about to just appear. So let's just pause that. You just missed me ramble about Stephen Hawking. So I took the initial value, set it up, solved for X. X is hydronium. There's my pH. Why am I not worried about the second reaction and the hydronium in there? It's going to add some. Plus Y. But Y is so tiny. Why bother calculating it? This actually ends up being the value for Y. The Ka2 ends up being the value for Y that you're adding to it. And the amount of hydronium from the first part plus 10 to the minus 12 is really just the first part. So we've hit all of the major concepts you definitely need to practice.